what's the difference between gene theory and the mitochondrial metabolic theory? Oh, and by the way, I'm the guy that bought your book.
Oh, yeah. Well, thank you very much for that. The book seems to be selling quite briskly now, far more than it did when I first published it. It was unbelievable.
Yeah.
So, yeah. So, well, that's the key. The most important question right now is cancer a genetic disease, or is it a mitochondrial metabolic disease? And it's actually no different than the controversy over the geocentric versus the heliocentric origin of how planetary celestial bodies move. Don't forget, for centuries, people thought that the Earth was the center of the solar system. The geocentric concept of Ptolemy and Aristotle and these guys. And then the Copernican revolution changed the way people think about that. I attribute this new view of cancer to a very similar kind of thing. Even more important, because if you thought the Earth was the center of the solar system, it wasn't linked to hundreds of thousands of people dying each day as the result of you're not convinced that the Earth is that the sun is the center of the solar system. So, but when you say cancer is a genetic disease, when there's massive scientific evidence to say that it cannot be, based on gene expression profiles, looking at all the different ways, the nuclear transfer experiment, all these different things coming together, evaluated carefully, says cancer cannot be a genetic disease. Driven by gene mutations, for sure. Do cancer cells have gene mutations? Absolutely. Where do the gene mutations come from? They come from damage to the inefficiency of oxidative phosphorylation. So yes, we look at the facts. Cancer cells have genetic mutations. We also know that there are germline mutations in families. These are called germline inherited as opposed to somatic mutations. They are secondary risk factors. They're not primary risk factors. So, and we know that every major germline risk factor, whether it's a Li-Fraumeni, which is the P53 mutation, or the BRCA1, or any of these kinds of things, they all, in one way or another, make mitochondrial energy efficiency less efficient. It affects mitochondrial function. So we have not yet found any cancer cell that does not have some abnormality in the number, structure, and function of the mitochondria, the energy generating organelle in the cell. We have found no cancer cell that can survive without fermentable fuels. All cancer cells, for the most part, have storage of lipid droplets, which are a biomarker for inefficient oxidative phosphorylation. So when you put that together, it clearly says that all cancers that we have evaluated, all major cancers, have some sort of defect in their ability to generate energy using oxygen. So consequently, they're all very, very similar in a dependency on fermentation. Regardless of whether every tumor cell has different genetic abnormalities, but they're all fermenters. So you have to go with the common problem in the tumor rather than the unique differences that exist in every single cell of the tumor. And every single cell of the tumor is a different genetic entity. No two cancer cells have the same genetic constellations of genetic mutations. Yet, every cell in that tumor is fermenting in one way or the other. So the common problem in all cancer cells is a reliance on a fermentation energy rather than an oxygen-dependent oxidative phosphorylation energy. So clearly indicates that cancer is a mitochondrial metabolic disorder, not a genetic disorder. And moving forward with managing cancer and reducing death rate will come once the field accepts this idea that cancer is a mitochondrial metabolic disorder. So the evidence is there. It's just that people either ignore it or refuse to look at it.